Let's just see how many people we've got. So we'll kick off pretty quickly because there's a fair bit to get through. If somebody can just put a message in the chat letting me know that you can hear me. Yeah, we'll get straight into it. So this is basically an overview of the Victron range of MPPTs and of Shunts battery monitors. There's not a lot to the Shunts, so it'd be mostly talking about the MPPTs. And I won't be able to cover absolutely every single setting that you can do with the MPPTs because there's a lot, but I'll definitely cover the major ones. But if you've got any questions, just put them through in the chat. So we'll get going. So we're going to go over the product range of Shunts or battery monitors, and then how you go about choosing one. And then we're going to go over the product range of MPPTs, and I'm going to talk about what maximum power point tracking actually is, and how you choose one, and then how you would set one up. So the product range from Victron of battery monitors, you can see them all here. They all look pretty different, I suppose, but actually they're all essentially the same thing in that what these battery monitors are doing is they're doing two things. They're measuring current in and out of the battery, and they're counting that. And that's how they can tell the state of charge of the battery, because you've told them already what the size of the battery is, and they're measuring the current in and out. But that's going to get out of calibration pretty quickly and easily. So the other thing that they're also doing is they're tracking the voltage of the battery, and when the battery gets back up to a certain voltage for a certain period of time, and after the current has dropped to a certain level, it then goes, okay, well, the charge algorithm has finished. I'm going to reset to 100. And that's a pretty important part of it, and we'll go through that in the settings. But the way that that's basically their two functions electrically, I suppose, is to measure current and to measure voltage. And the way that they do this, and you can see on the right-hand side here, you've got this box that says BMV 700H shunt box. And that has a bit of brass in there, you can see, and then this one at the bottom, you can just sort of see the two terminals. But that's a big piece of brass as well. Basically, it's just a big piece of brass, and it's measuring the voltage on either side of that, and it knows what the resistance of this piece of brass is. And so by measuring the tiny amount of voltage drop on either side of it, it can then work out what the current is flowing through that little bit of brass, or bus bar, we call it. And so the earliest one, at least that I'm aware of from Victron, was called the BMV 700. And you can see the big piece of brass much clearer in this picture here. And you can see there's a little circuit board on here. And so it's measuring the voltage on either side. And then it had a really long sort of telephone cable, which went to this round dial, which was the display. And that's where all the calculations and things were done. And you'll see lots of these in boats and old solar systems. The early ones looked just like this, and you had to look at the little dial and do all the setting up on it. And then they brought out a Bluetooth version of this. Then more recently, they've put out the SmartShunt. And the SmartShunt has exactly the same functionality, but it doesn't have a display. All of the brain of it is built into the shunt, right on where that PCB is. And you just look at it on your phone, because that became the most popular way of doing it, and it made it easier to install. So this is what the smart shunts look like. This one here is the IP65 one, is a more recent addition. And then these two here are just different sizes of the normal smart shunt. And so they make a range of different size battery monitor shunts in terms of current. 500, sorry, it starts at 300, it's the newest one, 300, 500, 1,000, and there might be one more as well, maybe there's a larger one. Oh yeah, this one's 2,000. I don't think I've ever seen anybody use one of those, because I think if you're using 2,000 amps at 12, 24 or 48 volts, I'd ask you some serious questions about your system design. But I guess there's some applications where it might be warranted. With the older style ones, you can actually take the shunts off and swap them for different sizes and things like that. And then after that, you've then got these other two types of battery monitor, which is the Lynx Shunt and the Lynx Smart BMS. And these are pretty much the same principle. They're just a slightly different housing, and they're designed to work with Victron's range of bus bars called the Lynx range. They have the Lynx power in and the Lynx distributor, which are a really handy set of bus bars, and they just bolt on the side here to each other, so you can sort of have as many of them going on along as you like. The one to note with this is the Lynx Shunt. You normally need to purchase a fuse with that, and you have to purchase that separately, and that goes inside it. And then the Lynx Smart BMS, this is only to be used with the Victron range of batteries that don't have an internal BMS. So you can't use it for other batteries and things like that. These shunts are really popular with lead acid batteries and gel batteries, and then unmanaged batteries like Power Plus. Also, they're really popular for that. If you have a managed battery like Discover or Pylon Tech or ZYC, then you don't need a shunt most of the time, because the battery is already telling the system what its state of charge is. And it does that in exactly the same way. It measures the current in and out of the battery, and it also does that calibration when it gets to the top of the charge by looking at the voltage as well. It's always measuring on the negative, and then it just has a key to the positive to power the circuit, and also so it can read the voltage properly as well. But you can also use these battery monitors as just normal DC energy meters as well, and I'll show you that in the settings in a moment. And that could be quite a useful feature. So this is how they're wired up. We've got, say, an MPPT charger coming in here. We've got our battery here on the left, and all you're doing is we've got the negative coming down from the MPPT, and it's going to the shunt, and then on the other side of the shunt is the battery, and then we've got the loads coming out here. So it's really important that you don't have anything on the battery side of the shunt over here on the left other than the battery. Otherwise, that stuff won't get measured. So you see that every now and again when these get installed, and people are sort of complaining that it's going flat when there's nothing happening, and then you look in there and you see that actually some of the loads are directly to the battery, and so the shunt's not measuring them. And then on the positive side, you've just got this little cable coming down from the middle here, going to the battery, and again, that's to power it, so it can do its calculations and things like that, and also so it can measure the voltage too. On some of them, there'll be an additional little input here, which allows you to either measure an additional battery, like the starter battery in a dual battery setup in a car. It can be used to measure the midpoint, and I think I've got a slide about that a little bit later on. And it can be used for temperature sensor sometimes as well, I think. But midpoint is the main thing you would use it for in big lead acid 2-volt battery systems. You don't see that as much now with all the lithium batteries. So this is what the interface looks like. I don't imagine anybody will be buying any of the ones that don't have Bluetooth. They probably don't even sell them anymore. But in the interface here, you've got the state of charge of the battery. And then on the right-hand side here, you can see what the voltage is. If there's any current, it will show it there. And then the consumed amp hours. And if it's able to calculate it, it will give you the time remaining. And this one here, in this example, they've also got a starter battery wired to that second positive input that I described. And so you can monitor 2 batteries, but only the voltage of the second battery. And then you've got history stats here as well, charge and discharge energy, total charge cycles, all that's quite interesting. The main thing it's useful for is if you look at what the minimum battery voltage has ever been and the maximum battery voltage. So say you've got somebody who comes in and say, oh, my battery's stuffed. And you say, okay, well, has your battery been charged properly? And they go, oh yeah, it's never been taken below 11 volts or below 12 volts or something like that. And then you can look at the history over here and you can see whether that's true or not. So that can be a useful thing for diagnosing issues. Now in the settings here, this is a really important bit to make sure that the battery monitor is going to operate properly. So the most important thing is the battery capacity. So if you've got a 200 amp hour battery, you need to tell it it's a 200 amp hour battery, because then it knows that if it sees 200 amps or 200 amp hours having gone through the shunt, if it measures that, it knows that it should be down at 0%. If you put 400 amp hours in there, it's going to read 50%. So it's important to get this value correct. And of course, that's always just going to be on the spec sheet of your battery. I'll come back to the charged voltage in a moment. The discharge floor, this is basically so you can have the actual capacity and then the usable capacity of the battery. So say we have let's say it's a 100 amp hour battery to keep the maths easy, but we only ever want to use 80% of that. So we're acting as if it's a 80 amp hour battery, so that we only ever take it down to 20%, so that the battery has a good, nice long life, doesn't get over discharged. So we can put that discharge floor in here. So we'd put, say, 20%. And so those calculations, when it says it's at 0%, what it means is it's actually at 20%. And so different types of batteries, you're going to set that up differently. Lithium, you're going to set it very low. Sodium, you would set it very, very low, like 5% perhaps. Lithium, you might set at 10 or 20%. And then a lead acid battery, you would set it quite high, so tubular plate gel batteries and old off-grid systems, you would usually be cycling it down to 30%. So you might set it at the discharge floor at sort of as high as 60% perhaps. So that's a really important value as well. The rest of these values are less important, but it is good to understand what they are. The main one we're interested in is the charged voltage. And so remember I said before that the battery monitor needs to recalibrate when the battery, a set of conditions that need to be met for what it decides is fully charged. And remember, we're talking about renewable energy systems. So we're not talking about something which is mains connected most of the time and has a really reliable charge source. So the charged voltage, it's easy to make a mistake when you're setting this up and put that as the absorption voltage, say 14.4 for a 12 volt battery. Actually, the default value, 13.5 for 12, is about right, because this is the voltage that it's going to reset to 100% when it sees that voltage. But it's not just when it sees that voltage, it's when it is at that voltage and then we go down to this setting we've got here, charged detection time. So when it's 13.5 for 3 minutes and the current is 4% of 200 amp hours. That's what we've got, the tail current here. So that would be 8 amps, right? So that lets it know that basically it's at the end of the absorption cycle, because it's reached this certain voltage and the current has got low for a extended period of time, and that lets it understand that you've probably finished absorption and are in float. That's what it's trying to detect. I can see we've got a question here. Let's see what the question is. Is there a shunt between the battery and the MPPT? Do I still need, if there is a shunt between the battery and the MPPT, do I still need a battery protect? Yes, normally you would. A battery protect is a different piece of equipment. The battery protect is a low voltage disconnection device. So that's designed to turn a load off if the battery voltage gets too low. The battery monitor isn't doing that. It can have an alarm when the battery voltage is low. There's a setting for that, but it doesn't actually turn anything on and off. It's just sit there. It's just a big dumb piece of brass that's measuring what's happening. It's got no switch gear or anything at all. It just tells you what's happening. It can send that information to the Cerbo, and the Cerbo can sometimes turn things on and off. But by itself, the battery monitor doesn't do that. And again, with the MPPT, usually the MPPT can't do that either, except the small ones that have a load terminal, and I'll show you that in the next section. But mostly if you have DC loads, then you need to have a battery protect to switch that off when the voltage gets too low. And it's separate to this. So charged voltage, tail current, and charge detection time. When you set this up, you don't normally need to change these values. The default ones are usually fine. People like Power Plus have custom ones, and so you can change it to theirs. But I'd recommend not changing them. The main place that people go wrong is they change the charge voltage to the absorption voltage, and that's too high, and it means it will never get to 100%. The P-Curt exponent, all that means that's just an algorithm for, when I say the battery is 200 amp hours capacity, that's usually at a certain rate of discharge, say C10. And so that means over 10 hours, you would get 200 amp hours out of it. But over a different duration of discharge, you would get, over a longer duration of discharge, you would actually get more amp hours out of that battery. In lead acid batteries, that's a really dramatic feature because of the chemistry of them. In lithium batteries, it's not as dramatic. The rate of discharge doesn't affect the amount of available stored energy anywhere near as much. I think it's 1.1 normally for lithium, and then 1.25 for lead acid. But it's not something that you need to stress too much about. Charge efficiency factor is just how much of this charge is actually going into the battery. 95 is the default for lead acid, 99 for lithium. And the rest of these values I'm not going to go into. You can recalibrate the shunt if you need to. You very rarely will need to do that. If you do need to recalibrate it, if you're looking at the shunt's values and you know there's 10 amps coming out, but it's reading 8 amps, then what you need to do is you need to remove the negative connection on the load side of the shunt so that there's no possibility of any current flow, and then you press the 0 current calibration in the app here, and that will calibrate it. You can also synchronize to 100% as well. Again, sometimes you might need to use that feature, but most of the time, I think you're going to, you're better off just to let it charge all the way up, and then it will calibrate itself. And so the last thing I'm going to mention with this is that you also have this function called battery monitor mode. And so you can actually, instead of having it as a battery monitor, you can change it to a DC energy meter. So if you're just using the shunt by itself, I'm not sure what application you have with it for this. But when you're connecting it to a Victron Cerbo, for those of you who don't know, Victron has a modular system, and a Cerbo is basically a brain device that will talk to all of their various products and put everything together for you in a nice interface and show you all the power flows and things. And I'll do a webinar about that later on in the year. You can use this to monitor just say one particular DC load. And when you change it to DC energy meter in here, you can then also choose from a bunch of types of energy meter like pump and a few other things. And then it will come up as that. Instead of coming up as a battery monitor on the Cerbo, it will come up as a DC energy meter, and it will show nicely on all the graphs. and things like that. So that can be quite useful for some things because you can then turn things on and off according to those values. And then if you were to use those other functions I was talking about before for that second voltage input, they're just set up here in the miscellaneous section of the settings, starter battery, midpoint, or temperature. That's an example of what midpoint wiring looks like. You've got two 12-volt batteries in series, and you've got the shunt wired on the negative like we described before, and then you've got one positive going to the main positive connection, and then you've got another one, the second one, going at the midpoint in between the two batteries that are in series. And so what it's looking for there is it's checking that the batteries, so they're both two 12-volt batteries, that both of them are exactly the same voltage. Say if the total voltage is 14, so we'd want both of them to be exactly 12. If there's a variation, then we know that they've got out of sync, and you'd get a little alarm, and you'd go in with a battery balancer of some description to get them making the right spot, because otherwise one's going to be overcharged and the other one's going to be undercharged. This is what it looks like when it comes up in the Cerbo. So the Cerbo is the brain device I just mentioned before. And in some circumstances, you might want to tell it to use this battery monitor as its main battery monitor, because if you have, say, a managed battery connected, or you have the battery monitor enabled on the multiplus, then they'll all show up, and you can decide which one you want to be the main battery monitor. So that's in system setup. Normally it's set to automatic, but you can change that, and you can see there's a bunch of different options here. Normally, if you had a managed battery, you would use that rather than the shunt-based battery monitor, but sometimes you might choose not to do that. And then when you're looking at it on the Cerbo, you can see all of this information here, the same as what you would see on the app. There is a function, if you're not using a Cerbo, called V Smart Networking, and this is a way of Victron devices to share information via Bluetooth. So you don't use this if you're using a GX device. I've heard conflicting things about this. Some people have told me they have done it with a GX device, but I've seen other people who have had a Cerbo or an Acrano and smart networking, and that has caused some stuff not to work. So you shouldn't need to use this if you're using a Cerbo, because all your information is going back to a central point. But if you don't have a Cerbo, you can, and say you have an MPPT and a battery monitor, and you want the MPPT to use the voltage that the battery monitor is sensing because it's more accurate, because it's closer to the battery, then you can connect them together with V Smart Networking, and they can share their information. You normally use it with this Smart Battery Sense, which is a small little thing which sticks right on the battery for giving you accurate battery voltage in systems. I'm not going to go into how to set that up today. It's pretty self-explanatory. You can just follow the instructions in the app. And then just quickly, these are just common things that people get wrong with the battery monitors. So they wire the loads on the battery side of the shunt instead of the load side of the shunt. So it has a battery side and it has a load side. You need the battery on that side and you have the loads on the other side. If you get it the wrong way around, the values will be back to front and it won't work properly. People sometimes run SmartShunts as a DC load meter without a main battery monitor. They set the discharge floor wrong, they set the capacity wrong, they wire the voltage sensor to the starter battery, and the other one I've seen, sometimes for some reason people don't use these big bolts on the top here. They connect using these little screws on the side. With most of the more recent battery monitors, it's not possible to do, but if you do have one of the older style BMVs, you don't use these two screws here. That won't work properly. Okay, MPPTs. So I thought I'd start with just describing quickly what MPPT is. So MPPT stands for maximum power point tracking. And what this means is that when we have a solar panel, it has voltage and it has current output. Now, if I take my solar panel and I don't plug it into anything, I've just got the two positive and negative cables here in my hands, then it's open circuit. I've essentially got infinite resistance between these 2 points, right? And then I'm going to have voltage, but I'll have no current, right? And that's what we're seeing on the left-hand side. If I short it out, then I'm going to have essentially zero resistance. I'm going to have no voltage, but I'm going to have maximum current, right? And so then if I have a little bit of resistance in the circuit, then I'm going to get voltage and current. If I have a high resistance, you can see on the left-hand side here, I'm going to get a lot of voltage, but not very much current. And then if I have some resistance, but it's very low, the voltage is going to drop down, but my current is going to be close to the maximum available. P equals V times I. Power is equal to voltage times current. We want to get the most power out of the solar panel. So our power is equal to our voltage coming out of a panel and our current coming out of the panel. We can see down here that 22 volts times half an amp. Oh, okay, so 22 times 0, if I've got maximum voltage and no current, 22 times 0 is 0 watts, no power. And then 0 volts times 5 amps, that's no power as well. But if I've got 22 times 0.5, that's 11 watts. Or if I've got 5 times 4.5, that's 22 watts. So that's twice as much power. So the amount of resistance that we present to the circuit for the solar panel has a big impact on the ratio of voltage to current. And so if that resistance value isn't correct, we don't get the maximum amount of power out of the solar panel. So that's fine. The perfect spot for this particular panel is where the voltage is at 18 and the current is at 4. And that gives us the most power out of this panel. If the solar panels just were the same all the time, we wouldn't need to be talking about any of this, because somebody much cleverer than me would have worked all this out and would just have a fixed resistor on their MPPT and to get the most out of the panel, and you wouldn't need to worry about it. But because solar panels are determined, their output is determined by the irradiance of the sun, the angle of the sun, and the temperature of the panel, this sweet spot changes all the time. And so what we need is a device that actually can vary the input resistance of the MPPT according to the conditions in order to always get the most out of the solar panel. And that's what maximum power point tracking is. So you can see we've got all these different periods of the day, different angles of the sun, different amounts of irradiance. The sun is going through different amounts of the atmosphere, and the temperature is changing. And so we constantly need to be changing that value. I'll just go back for a moment. And so the MPPT is calculating that all of the time and updating, and it scans the entire range. And that makes an enormous difference. So PWM charge controllers, they don't have maximum power point tracking circuits in them. And so they don't harvest anywhere near as much energy from the solar panel as an MPPT does. So it used to be the case that MPPTs were very expensive and only sort of big fancy systems had them. But now the prices come down a lot, that hardly anybody uses PWM charge controllers anymore. But you still see them out there, the Plasmatronics range, you'll still see on legacy systems. And they're still good pieces of equipment and suitable to be used in some circumstances. But because MPPTs are affordable now, that's what you'd use most of the time. Now, the other important thing to know about this, and goes for all charge controllers, not just MPPTs, is that the circuit needs headroom in order to do its job. So we've got a 12-volt battery. We need to charge it up to 14.4. That's at our absorption voltage. If we don't have 14.4 volts coming in, then we can't charge the battery up to that. And actually, we need more than 14.4. We need headroom because there's losses in the circuit, right? So you need at least 18 volts coming in to the system in order to charge a 12-volt battery. This is why if you have a 24-volt panel, you can't charge a 48-volt battery because that panel isn't putting out enough voltage to charge the battery up. These MPPTs don't have a DC to DC converter to boost the voltage back up again. You have to have voltage headroom. It can only step it down. And so this is just a little illustration of that same point as well. You're going to have losses. If you put 14.4 into our circuit, then you're probably only going to get 10 volts out. So really you need 18 volts to get your 14.4 out. And that leads us to, hopefully that makes sense. That leads us to the range of Victron MPPTs that are available. You can see this is a pretty long, boring list, but you can look down the side here and you've got two values. You've got the first value, like say 75, and then there's a dash, and you've got 10. So the first value is the input voltage, the maximum input voltage. So this one, the first one here, 7510, you can put an open circuit voltage of up to 75 volts into that. And then the second value is the maximum current that it will put out. Now, because the input voltage is 75, that means it's basically only suitable for 12 and 24 volt battery systems. If you want to charge a 48 volt battery system, you have to go down the range here until you get to an input voltage of 150. So you've got enough voltage headroom to charge a 48 volt battery. It's fairly self-explanatory throughout that range, other than that you can see that some of them say VECAN next to them. And that means that they have two different options of communicating with the Cerbo, and I'll show you that in a moment. There's two different types they make as well. I'm only showing the smart solar ones, which are the ones that have Bluetooth built in. They also confusingly make a range called Blue Solar, which do not have Bluetooth. I don't really recommend you ever buy the Blue Solar ones, unless it's on some sort of security application when you don't want someone Bluetoothing into it remotely, because it's just so useful for being able to set it up. And you can change the Bluetooth password anyway. So I think you should always just buy the smart one. So this is what I was talking about here. You've got 75 as the voltage input limit, and then you've got the second value is the maximum current output. And obviously in a 12 volt system, you're going to get 15 amps of current, but if you're using it on a 24 volt system, you're still going to have a maximum of 15 amps, but that's at 24 volts. So actually the power is doubled. So you can put a much larger array onto that system. So the 75 and the 100 range, they're suitable for 12 and 24. And then you've got the 100, 150, and 250 range, which is suitable for 12, 24, 36, and 48. And then you've got the 450 input range, which are only suitable for 48 volts. And you might have picked up that there's a bit of a discrepancy here, that these ones on the left, the 100/50 doesn't do 48 volts, but this 100/20 here does. And that's a special part of the range that they made for that. But you still need to be careful that you have enough input voltage from your array to charge a 48 volt system when you're using this. If you don't, then it's still not going to work. The other features of the product range are that the smaller ones have a load terminal. So this comes back to what Derek was asking earlier about a battery protect. which is that the load terminal built into these small ones has a low voltage disconnection feature. So when you set it up, you can program it according to various functions. Normally it'd just be if battery voltage gets below a certain point, then it's going to turn off the positive connection on here. So you're going to wire the battery into this far left 2 terminals, your solar panel into the middle 2, and then you can put your loads here and it will turn them off and on according to the battery's state of charge or voltage. And that stops you from running your battery flat. So that's really useful on small systems, again, like security cameras and things where you don't want to have separate bits. It's just an all-in-one device. But when you get larger, then the current is too large and you wouldn't want to have it done internally like this. So it's the largest that they make in this format of having the 6 terminals is the 100/20. And after that, it's in the style that we have on the right-hand side here. And it doesn't have a load port. It's just got a battery and it's got a PV port. The smaller ones also have a built-in fuse, which is handy as well. And that's just protecting the battery terminals. And then as you go up the range, there's some more features added. So these larger ones here, the 150, starting with the 150/70, they also have a relay built into them, a programmable relay. And then they also have a remote. So the remote is just a way of turning this off and on with a switch. So you can see, you can't really see it very well. On the right-hand side here, you can see it well. It's just a little jumper, goes from one side to the other side. So if you pull that out, it will stop working because it needs to connect one side to the other side to operate. So what you can do is you can take that little jumper out and you can wire that with a bit of twin cable to a switch that you have somewhere else. And then when you flick the switch, it goes open circuit and the MPPT will turn off. It's also used with some dry contacts on batteries BMS. If they want to be able to tell the MPPT not to charge anymore, they can run their dry contacts through this. And that's a way of the remote controlling the MPPT. And then you can see the VE CAN is the ports at the top. And so that just means that you can connect it to the Cerbo via CAN bus instead of by doing VE direct, which is the standard one on the left-hand side here. And there's no real advantage between VE direct and CAN bus in terms of the information. The only reason is that you might want to use it is because if you've got lots of charge controllers, VE direct, you have to have one cable to the Cerbo for each one, you know, so if you had 4 of them, you'd have 4 cables and it's going to get messy quickly. Whereas you can daisy chain the VE CAN connections and have other VE CAN, not just MPPTs, on that same connection. So that can be a bit neater and more efficient. But other than that, there's not a lot of difference between them. So the largest that they make is the RS range. With a 450 volt input. They make a 100 amp and a 200 amp version of that. And it's pretty similar, but it just looks quite different. Again, it doesn't have a VE direct port. It only has VE CAN. It doesn't have a load port. It has multiple MPPT trackers in it, so multiple channels. So you can put different strings of different voltages into those channels. It has a remote switch. It has a relay and voltage and temperature sensing. Yeah, and there's not a lot more to say about that one other than that this has built-in earth guard protection as well. So you don't need to put in, say, an AERL earth guard with these because they have that built in, whereas the rest of them, if you're over the voltage threshold, then you need to put in an earth guard of some description with the smaller size ones if you're over that voltage threshold. So that's the range. Basically, I'll just explain about that just one more time so people understand how to size the array, I suppose, is that the first value determines the voltage that you can put into it. So that's your string voltage. So if you've got a big system, you want a large, unless you want to run them in parallel and have large current coming off the roof, you normally want to run pretty high string voltage. So you can just have one pair of cable coming down off the roof. But the second value is the current output. And so that is going to determine the size of the array that you can install. So for instance, let's have a look. We've got the 150/70 here. So say we have a 48 volt lithium battery, which is going to get charged up to say 55 volts. So we multiply that by 70 amps, and that's 3,850 watts. So that's the size array that would be suitable to use for that at 48 volts. If you're charging a 24 volt battery, then it's going to be half that, because it's going to be 70 amps times whatever your 24 volt charge voltage is, say 27.5. Because it's able to manipulate the input resistance, that means, and we saw before, that the input resistance, the higher the input resistance, the less current you have. It's manipulating the amount of power coming out of the array. Within reason, you're not going to damage the MPPT by putting a larger array on it than that calculation that I showed you. You can sort of put as large an array on as you like within reason. And it's just it can just throttle it off if it doesn't have any use for it. It can just make its resistance high, and then so there'll be no current and there'll be no power. But if you put too much voltage into it, then you will break it, because the components have a set voltage range. So there's a calculator on the Victron website, which will help you work out your string voltages and what size MPPT to use as well. But normally your open circuit voltage, you want to have sort of 10% below the top threshold, because that open circuit voltage on the spec sheet is in standard test conditions. If the panel is really cold and gets sudden burst of light, then that voltage can be higher than the open circuit voltage. So you want to give yourself a little bit of wiggle room. Don't design it to be bang on the top value, because you will break it. So when we're setting it up, this is what our interface looks like. Again, we're connecting with Bluetooth. Download the VictronConnect app, connect to it with Bluetooth. You can do it direct to USB on your computer as well if you want to. This is what the main interface looks like. You can see it will show you the amount of wattage coming out of the solar panel. It will show you the voltage and the current. And it's showing us here, we've got a solar voltage and a solar current. And then you can see below that, you've got the battery voltage. And if you were to scroll down further, you would see what the battery current is. And obviously the solar voltage is going to be higher, and it's going to step it down to a lower voltage. And then the current will be proportionally higher because it's converted it. Both values should add up to the wattage that we see here. Something that happens every now and again is somebody will say, I've got a 200 watt panel, but I plug it in and it's not saying 200 watts, even though there's full sun on it. But if there's nowhere for the energy to go, then it won't produce it. So if the battery is full, then it's not going to say 200 watts. It's just going to say, 0 watts or 5 watts for its float charge or something like that. So it will, if you then turn on a load, you'll see it go back up again. On the right-hand side, you've got the history tab. This is quite similar to what I was talking about with the battery monitor. You can see the minimum and the maximum battery voltage for each day. And that's really useful for troubleshooting. And then you've got what the maximum yield has been for each day, so the total it put out, and then what the maximum the panel actually put out on each day. So that's really useful if someone says that their array isn't working, and say again it's so let's say that this person has a 1.5 kilowatt system, right? And we can see that each day it's put out about 1.5 kilowatts, right? As its maximum. And then you can see the total that actually harvested during the day is the yield. So you can see that it is capable of putting out that amount. It just didn't do it for very long, or it did do it, and it's all working nicely. But if you see that it's never getting anywhere near that Pmax value of the rating of the panel, say it's a 1.5 kilowatt array, but our Pmax value is say only 200 watts, then that might mean that you've got some shade on the solar panels or something like that, because it's never putting its maximum wattage out at all during the day. And then the Vmax is a similar thing. Your Vmax should be something close to the VMP of your array. And if it's a long way off that, that would indicate that you've got a bad connection or something like that. The other thing that I sometimes see as well is that if the battery actually has a, say the fuse blown or something, and the MPPT is just running as a power supply during the day, and you haven't noticed, you can look at the minimum maximum battery voltage, and you'll see that the maximum might look pretty healthy, but the minimum every day is say 0 or 2 or something like that. And unless the battery is completely stuffed, that actually means that it's just falling over at night, because there's actually, the MPPT is not actually connected to the battery. That happens more often than you think, that somebody's working on a site and they haven't noticed that the fuse or the breaker to the battery is actually blown, because it's just running direct off the solar. So we have the settings here. So you click the cog in the top right-hand corner, and we go to the settings, and we're mostly interested in the battery settings because it's mostly a battery charger. And that's what this looks like. The first thing you'll notice here is the battery voltage. So this is an important one. It does auto sense the battery voltage, but it can only do that if you connect the battery first and then the PV second. If you connect the PV first, then it's going to, you know, just decide what it decides, and then it will be set. And every now and again, people will turn on the PV first and it decides it's a 12-volt battery, and then they turn on the battery and it's a 48-volt battery, and then it goes, oh, the battery is way too high in voltage, I'm going to go into alarm state. And I'll show you a bit further along about how some of them will actually short out the PV input terminals to protect the system, and so you'll need to undo that. So wire up your system, turn on your battery first, don't turn on the array, and then set the battery voltage to whatever your nominal battery voltage is. The max charge current, you're not normally going to adjust this unless you want to throttle the array for some reason. And then charger enabled, yep, you probably want it to be enabled most of the time. And then we've got presets. You can see here it says rotary switch. That's really a pretty old feature. You might have noticed it on some of the pictures I showed before. Oh, we've got a question here. Carl, the RS450 has a V-direct port as per the data sheet. Okay. So the rotary switch can be used for setting some of the presets, but I think you'd normally just use the app here. And so you would change that to, there's a selection of presets in there, or you would change it to user defined. And so let's have a look at those. The ones that I recommend people use most of the time are, I don't usually recommend people use the settings, the presets that they have, unless you have some sort of unknown battery. I think you normally want to set it according to the battery manufacturer's instructions. But what I would recommend you do is you go into the battery presets and select a preset which is of the same type of battery that you have, and then go and edit those. And that will convert it from being a preset to a user-defined setting, but it will be set up, the template will be there for you. So if it's a tubular plate gel, it's going to have all the equalization options that you need for a tubular plate gel, and then you go and check those against the manufacturer's instructions. If it's lithium, it's going to turn off automatic equalization. So most of you are going to be using lithium batteries. So you go in and just select the lithium preset, And then you're going to click on these values, the absorption voltage, the float voltage, and you're going to set those according to the manufacturer's instructions. And you'll see that the little definition here will go from preset to user defined when you do that. That's the quickest and easiest way of doing it, rather than trying to figure out what all these extra settings are that your battery manufacturer hasn't given you values for. There's also this area called expert mode. You're not going to need to use this most of the time. This is basically determining when it's going to go back into absorption. So when you have a charge algorithm, you're going to charge the battery all the way up to, say, over here we've got 28.8, and when it reaches 28.8 and has finished putting as much current as it can in at that amount of at that voltage, then it's going to stop charging it and it's going to hold it at 27.6, which is our float voltage, right? It's not going to go, oh, I'm below 28.8 and go back up to 28.8 again. It knows that it's in float, and it's just going to hold it at 27.6. The reason for that is, imagine you have some lead acid batteries. If you brought them all the way up to the absorption voltage, they're going to sort of be gassing off and bubbling and things like that. You don't want to be doing that because you're going to dry them out. So you then, once they've finished absorbing, they then get held at this lower voltage where they're still full, but they're not gassing off, right? But then at some point you need to determine, well, the voltage is going to fall below that. At some point, I want to start the algorithm again. I don't want it to keep going round, round, and round. But once the battery voltage gets to a certain lower set point, then we restart this algorithm and bring it all the way back up to the top. So that's what the expert mode is mainly for changing. And you don't need to change this most of the time. So the rebulk offset is saying 0.4 volts below float is when it's going to start its little algorithm and go back into absorption mode again. You don't really need to mess with this most of the time. You'll know about it if you do. So I wouldn't recommend doing that. There's a few other options in the settings here. I'm not going to go into them in a lot of detail, but basically the V-Direct port can be used to communicate with other devices if you wanted to. Normally, you would have it with a Cerbo these days and do any sort of clever manipulation with the relays and with Node-RED. But if you're doing a more basic system, then you can use some of this functionality. And so the TX port function is when the V-Direct port can like do a pulse output to some other type of energy meter to show how much power is being produced. The RX function is when you can have it connected to a BMS and turn it on and off. If it's one of the smaller ones that don't have a remote, like I explained earlier. And then you've got the relay options. So on the larger models, I showed you that they have a relay. So you can set up the relay to turn on and off according to various settings that are available here. I think that's reasonably self-explanatory. And again, you can add it to Smart Networking as well. In the same way you can with the battery monitors. Again, you might have something like a Smart Battery Sense, which is an external battery voltage and temperature sensor, which sits right on the battery, and that can give the MPPT a more accurate battery voltage level than it can get because it's only reading it at its terminals. In managed systems, the MPPT is going to behave a little bit differently. So a managed system is when the Cerbo is getting information directly from the BMS of the battery. And in that circumstance, the battery is sort of controlling the Victron system to a certain extent, telling it when to charge, when to discharge. And so it's taking the control away from the internal set points that we've just done on the charger, and it is telling it what charge voltage to take it up to and what its maximum current is and things like that. So when you connect to it and it's in, the Cerbo is automatically going to detect this BMS connected battery, say Pylon-Tech, and it's going to automatically put the MPPT into networked or external control mode. You can reset this remotely if you want to, but it will revert when the Cerbo will just put it back again after X amount of time if it still sees a managed battery connected to it. The main thing to know about this is that even though the Cerbo and the BMS are taking over responsibility for what the charge voltage of the battery is, you still need to set the MPPT's voltages anyway. And that's because it can lose comms to the battery, and it's supposed to then stop charging when that happens. But actually, if the whole system powers down and then boots back up again, then it will just start charging according to its settings. And then it could overcharge the battery if you haven't got them set up. So you should always set these according to manufacturer's open loop instructions anyway. And the same goes for the inverter as well. You should always set it and not just rely on the managed system. This is what it looks like when it's in networked operation. So when you go to it on the GX device, you can see that it's an external control, BMS control, yes. If for some reason you want it to stop doing that and use its internal settings instead, you can press reset. So an example of that might be when you have a system which has lost its ability to communicate, but the battery is still operating, but the MPPT is not charging it. Then you might press reset and it will start charging the battery and wake the battery back up again. And so this is what it looks like in the Bluetooth app. You can see BMS controlled is in the bottom right-hand corner down here. And so finally, some tips and tricks. This is what I was talking about before, the input short circuit reset. So basically, if the MPPT, and this is mainly in the larger models, although I think they're starting to roll this out with the smaller ones as well, if it sees the battery voltage as being way higher than it thinks it should be, then it will short out the PV input terminals so that it doesn't cook the batteries. This usually happens during commissioning when somebody has not set the battery voltage correctly, and they've, say, turned on the PV first, and then it thinks it's a 12-volt battery for whatever reason, and then you connect a 48-volt battery and it goes, whoa, and it will short out those input terminals. If that happens, what you need to do is you need to turn everything off, and you need to get a 12-volt battery and connect it to the MPPT, and then go in with Bluetooth and go into the product info section, and then there'll be an option to reset the PV input short circuit relay. It must be lower than 15 volts, whatever battery you use. So if you're doing big 48-volt systems, sometimes people have to use their car battery. It's a good idea to have a little 12-volt battery kicking around for this type of thing. There were, in the early days when this feature first came out, there were some that were kind of faulty that would do this kind of randomly, but I haven't seen that for a while. So normally it only happens now if you make a mistake with your commissioning. It also might happen if there's over voltage from the array as well. This is what it looks like. So you just go into the settings, and there's 3 little dots in the top right-hand corner. Press those to get to the product info section, and then the reset button will be down there. Things not to do. Don't connect one array to 2 MPPTs. So don't have one solar panel and feed it down to 2 MPPTs. That will make it catch on fire. Don't turn on the PV before you set the battery voltage. Don't run your load terminal as always on, because that defeats the purpose of having a load terminal on your MPPT. Sometimes people expect the load terminal on the smaller MPPTs to be a regulated voltage. It's not a regulated voltage. It's just a switch inside. So whatever the battery voltage is will be what you will get out of the load terminal. It won't be exactly 12. It will be whatever the battery voltage is. But nearly all equipment that you would be running, such as a security camera, is actually, if you look at the spec sheet, is designed for a voltage window of about 10 to 15 volts anyway. So it doesn't need a regulated power supply. If you do need one, then you're going to have to get a Meanwell or something like that. Don't wire your array too close to the voltage limit. So again, we've got our 2 values. Say it's a 150/70. 150 is the voltage input limit. So don't design your array to be bang on 150 open circuit voltage. It needs to be, 5 or 10% below that. Again, you can go to the Victron website and they have an MPPT design tool where you can put your panel in and your string design and it will tell you. Don't forget to use a fuse on the output. Don't forget to program the battery voltage when using managed batteries. So again, that's when I say battery voltage, I mean the charge voltage. Bluetooth issues. So every now and again, people lose the Bluetooth code, the Bluetooth pin. And so you can actually reset it. And it has a thing called a PUK code, which is written in a sticker on the side of it. And that will allow you to reset the Bluetooth pin. But obviously, if you've got it installed somewhere awkward, that's going to be hard to get to see that sticker. If you can't connect to it, sometimes you need to delete it as a Bluetooth device on your phone and try again. It's also a good idea to have a V-direct to USB cable, and they make a USB-C one now as well. So that if you're having trouble communicating with it, the Bluetooth can be a bit finicky sometimes. It's a good idea to have a laptop or a tablet and a V-direct to USB cable, and that makes everything just run really nice and smoothly. And if you're updating firmware, that's much faster as well. Wiring issues, the common ones that I see are the negatives are common. So all the negatives on the, we're looking at the small ones with the 6 connections, then all the negatives are connected. It does it switching on the positives. So every now and again, somebody will assume that it switches on the negative, like old PWM ones do, and they will bypass the positive. They put all the positives together and then connect it to the negative, and then that just means that it's not operating. That's most of it, I think, really. Yeah. So if you have any questions, there is a question. Let's see, what's the question? Thanks, Mario. Yes, I'll send out the slides, and there'll be a recording of this as well. I'm going to be doing more Victron sessions on the rest of the Victron range, and I'll be starting off just basic like this, and then going into sort of system design things as well. If there's things that you would like to see, just let us know. Yeah, thanks for coming, and we'll see you next time.